Okay, I'm recording now. So when WP is high, this output is high. And so we're in this region right here. WP is actually going to shift this closer to VDD, which gives us better noise margins, and LP going down would do the same thing. So the size of the PMOS transistor affects that high when the output affects the VTC when the output's high. The NMOS transistor affects the VTC when the output's low. Okay. Now this is why area is important. We have a fixed cost per wafer, 10,000. Okay, good. It's just this. $10,000 seems rather cheap. No matter how big the die are and how many I can fit on there, I have the same cost. So if I can put more squares on here, if I could make these all squares, if I could make the circuits look like that and be a quarter of the size, I could sell 4 times as many product. Now there's another issue, and you see this at Micron or any semiconductor company, the yield heroes. I just discovered something about the process that makes the yield 0.01% higher. I've scored my big bonus for the quarter. Sometimes at Motorola, my bonus was bigger than my check, my regular check. So where yield is a problem is I go through, and the first thing I do when I get this wafer out is I test it. I put VDD and ground to the chip, and I measure the current. If the current's 0, I put a big black dot on it, and I never test it again. If the current is above a limit, I put a big black dot on it, and I never test it again. These are bad devices that I'll never be able to sell. And as you go through the processing, the tests get more elaborate based upon how much money they put into the device at that time, and they have to throw a lot of parts away. If you can make that yield higher, you've just gotten them free money. Yeah, think about your study skills. Think about what works for you and doesn't. Spend a few minutes doing that. That will help you be a better student. Everybody, freshmen are horrible students. They're just learning how to study on their own without having their parents and their high school teachers holding their hand. It's a transition. You get to be better students as time moves along, so then the coursework gets harder. Okay, we want to think about this. What happens to current as W increases? So this is the saturation current equation, but for all the current equations, if W, including triode, if W increases, ID increases too. So if I need, what does W do for me? It gives me higher current drive capability, which may be something that you need. You want to drive 10 different buffers off of this single device, then maybe I need a bigger W here in order to drive it, or I have to drive a lot of capacitance. It increases the speed. And I'm just going to declare that at this moment. Increases the speed. All of these are good things until you get to the thing right here. You have a bigger power dissipation, bigger area, and power dissipation. So it's a trade-off. You keep the W as small as you can to kind of meet your specifications. Okay, I'm not doing horribly. Now this is what a transistor, or this is what a CMOS inverter looks like to an IC designer. There's more elaborate stuff going on, but this is the basic part of it. What I'm going to do is I lay out this active area, and the active area is the P plus diffusion. So this is the drain, this is the source, and this red area is the gate. But the line we drive the gate with is a multi-purpose line. It both acts as a wire connecting these two transistors together, and it's part of the transistor. You only get transistors are only when, I don't know how many times I'll say this to you in the next 2 years. Transistors are defined by poly over active. So the actual gate of this transistor is this area right here. The other red part of that, and the red part is poly. The other pieces of the red part are used as wires to interconnect the two transistors. So if you think about this, this is the gate of the, I know this is P plus diffusion, this is the PMOS. Right, it's bigger too. And this is the NMOS. And if we look at the actual circuit for this device, it looks like this. I usually get myself in trouble doing this. The gates of the two are connected together. So this is where the gates are connected together. It's the interconnect. Now, if we want to figure out how big the transistors are, my W for the NMOS device, and I said the NMOS device is smaller, the PMOS device is bigger. And also the NMOS device has N plus diffusions for the drain and the source. So we want to figure out how big the transistor is. We measure the W of the gate, and it just goes to the green lines, is the W in that dimension. The L is in this dimension. And yes, you'll get to do that a lot in lab 4 in 380. And that is for the NMOS. For the PMOS, my W goes right here, and my L is the same. Typically, we make the W of the PMOS transistor about 2 to 2.5 times bigger than the NMOS transistor. We always use 2.5. You can get by with a little bit less. And that's because the holes move slower than electrons, because they're all bound to the atoms. So to match the speed between the two devices, we have to make the W of the PMOS transistors bigger. Now for those complex functions we looked at a couple of classes ago, something like this, each literal in here, if we think about this, is going to need one PMOS and one NMOS. I can tell you how many transistors this circuit is going to take just by counting up A, B, C, D. There's 4 letters in there. Some of them could be repeated, but I just count the number of letters. That's 4 times 2 transistors. And I can pretty much calculate in my head pretty quickly. I'm going to have to take, it's going to take at least 8 transistors to build that function. And if I come up with a circuit with more than that, I know I can reduce it. And if I can simplify the Boolean expression, I might be able to do it with a fewer number of transistors. Okay. And then in 380, we learn tricks to make the 8 go down to a fewer number. In dynamic logic, you can do it with 6 transistors. And past transistor, I'd have to draw it out, but you might be able to get by with 4. Yeah. Setting your goals, writing them down helps you to achieve them. You would be surprised. sometimes I just think of things that I really want to do and they sound kind of screwy. But as a little kid, I really wanted to go to Mars. And every time I would go out to play, my mom would ask me where I'm going. And I'd say, I'm going to Mars. And she'd say, okay, be back in time for dinner. And I'd go, okay. And I'd go out and wander around all over the neighborhood. And then, you know, and you just kind of keep that in the back of your head. And then suddenly the opportunity comes up to work on a Mars rover. And you're thinking, hey, you know, I might really be doing this. And it happens. And I also worked on another instrument too for Mars. I'm just going to skip this, but you don't care until 380. So delay in power. We want to start thinking about, this will be the last topic for today, unless we do the review. What happens as a function of time? Now, we've talked about the CMOS and the inverter, it's the input's low, the output's high, and it just stays that way. What happens if I want to change the voltage at the input? How long is it going to take to settle? So we got to figure out how fast it is. We want the delays to be as fast as possible, so we can download our cat videos in record speed time. We want the power to be as low as possible, so I'm not burning up the battery in my laptop while I'm doing it, and also so I'm not overheating my devices and potentially damaging them. So unfortunately, we want both these things. It takes more power to get faster delays. So we got to talk to people. We got to figure out what the spec is for the circuit, how fast they want it to run. Maybe I can find a little trick they'll make it run a little bit faster without consuming without consuming a lot more power. And you know, it's this constant trade-off and pushing that technology edge. There are tricks and there's reasons why we're using smaller devices to get to there is one more thing that you can do that will both will lower the power and decrease the delay, and that's make my transistor smaller. Now this is why delays are important. Okay, I've got some register here. Most of you've probably all taken 110. Yeah, there's no mechanical engineers in here this semester. We get mechanical engineering majors who have not taken 110. Occasionally get an EE major and I just kind of glare at them. Okay, so you've got a data register in here. And during this clock cycle, what's going to happen, let's say on the leading edge of the clock, we'll call this a leading edge trigger clock, this register is going to, my outputs are going to be valid. Then it's going to take some amount of time in here for my combinational logic to settle. So AND gates take picoseconds for the logic to run through them and get to the output. But the whole, we got to look at the block as a whole and find out what is my I'm going to call it, use the same terminology, that's why I'm looking down here, TPCL, the combinational logic block delay. And then in addition, and my clock's still ticking. And the other thing that is got to happen here is this register has some setup time associated with it. I've got to have all the inputs stable for so many picoseconds before the clock edge. Otherwise, my register may not clock the right data in. So this is called the setup time. And that has to happen after my outputs are stabilized. So it takes some time for the output to get valid. It takes some time to go through the combinational block. It takes some time to go through T setup. I've got to make sure, and this is the way we did it, but what we always did it was like this, that all of this stuff fit in the first half of the clock cycle. And that gave us a whole half a clock cycle of margin, because some of these devices in here are going to be a little bit bigger, some are going to be a little bit smaller, Some of them are going to be a little bit slower. Some of them are going to be a little bit faster. And to give myself guaranteed enough headroom, we would say my margin was 50%. And that pretty much guaranteed everything that would work. You can push that, but your yield might start going down. So as fast as I can get all of these delays, the faster I can clock my circuit. The faster I can clock the circuit, the faster I can download my cat video. There was a great one. My sister-in-law posted it, and both me and my best friend, like from 4 years old on, both said the same thing. We're cat number 3. There's first cat. There's the big array of cups. Sorry, first cat just very carefully goes through the array of cups. Second one goes through the line, and the third one just pounces in the middle of them, scatters everything. And me and Meredith like, hey, cat number 3. Okay, so we want to be able to quantify these delays and measure them. And I actually wrote them down, and I probably did this today, which ones are which, just so, because I will slur my letters and sometimes say things wrong. Coming up here, this is the input. And we know it's the input because the input happens before the output happens. The output happens as a result of the input. So this one is going off first, so this must be the input. Really easy way to figure this out. I put this on exams before and said which is the input and which is the output, and 3/4 of the class gets it wrong. Okay, on the input, we call the amount of time the signal takes to go from 10% to 90%. We kind of put those ranges on there because we want to make sure it's really changing and not noise, and make sure that it's really getting to finished. So this is called the rise time here. And this A is T rise. B is on the input. We go from 90 to 10. So this is T fall. Now we could do the rise and fall time on the output. Since this is an inverter, when the input's rising, the output's falling. My 90 to 10 on the output, we call that TTHL. And that stands for T transition high to low. And the only way I can keep these letters straight is by remembering the acronyms. And so transition time is like rise and fall time on the output. We have to give it a different name because otherwise you don't know which TR and TF it is. F is also a transition time. It's going from 10 to 90. And the output's going from low to high. So this is TTLH. Now there's 2 other times in here that are critical. And this is how long does it take the output to change how long does it take for the output to respond to a change in the input? So I make sure the input's really changing. It's up at its 50% level. And I know the output's really changing when it gets down to its 50% level. So this time C here is called the propagation delay. How long does it take for a signal to propagate through the array? So this is TP, and the next letters are referred to the output. So the output is going from high to low. So this is TPHL, and the other one, 50 to 50 on D, is going to be TPLH. You also will get to measure these in lab 6. You put an input delay on a signal, you do a transient analysis, you look at your output, and you measure the delay across there. This is a really good set of slides to have open in lab when we get to lab 6. This is the last week of lab in here. So we want to measure them. this is the diagram that's shown up on the exam. Don't know if it will this time or not. Which one is the input and which one is the output? The input's the one that happens first and is less messy. So this is V in, this is V out. Indicate, and this really surprises me too, indicate the 100 picosecond after the clock location. So I've got the clock transition here. The clock's probably, the clock may be transitioning here, but I'm just going to assume this is my transition right here. Assume things happen instantaneously. I've got 25 picoseconds per division, so 100 picoseconds would be 4 divisions later, so I just count out 1, 2, 3, 4, and go a little bit back. That would be 100 picoseconds after the clock location. And then each one of these, if I told you there were 1, 2, 3, 4, 5, 6, there's 0.3 volts per division. That means that each one of these squares is 0.3 volts. And we could measure those on here, but there is no way I can draw this on the screen. If you want to see this in gory detail, there is a really beautiful picture in the slide solutions where I actually go through and make the measurements and approximate them. Again, if I ask you to do this and you're not in the lab or you have the thing in front of you and you've got cursors and you can do measurements at the very different points, it's going to be an estimate. And if you're within, you know, like 20, 30%, I usually give you credit for it. Yeah. I have put that on exams too before. Oh, I have way too. Okay, good. Okay. Now, inside these MOSFETs, there's capacitors. If you think about the gate itself, the gate is a metal, then there's an oxide and a semiconductor. That's called a MOS capacitor. So there's other capacitors in there from other things that we'll talk about in more detail in 380. But this is pretty much most of the basic capacitors that people model and put into the multi-sim model of the transistor and put into the Mentor graphics and the cadence model of the transistor. They all have names. And yeah, Bob, George, this is the gate, this is the drain, and this is the source, and this is the body. So start out there. The rules for the naming convention is gate comes first, and this is all I ever need. Gate first, body's last. So going from the gate to the drain, this capacitor B here is going to be CGD. Gate comes first. Going from the gate to source, this is CGS. Those are the two largest capacitors in the device because that's the MOS capacitors. Going from the drain to the body, body comes last, so CDB. Going from the source to the body would be CSB. And going from the gate to the body is sometimes a very large capacitor too. Gate to body. I said sometimes. Turns out in the different regions of operation, these capacitors have different values. Some of the capacitances are voltage dependent. Think about trying to analyze this circuit by, oh, let's just go to the next slide. Think about trying to analyze this circuit by hand when you have to calculate the capacitances, take into account the voltage levels. The voltage levels are changing because your input's going from 0 to VDD. And you have to be grateful that you have things like Multisim and Mentor graphics to do this for you. But these capacitors are what drives how fast this can work. So if I can keep the capacitors smaller, I can make my circuit run faster. This capacitance right here is dependent upon routing. I have to take that into account too. And yeah, and they all work together. Ways I make, what is the capacitance? Remember, for a parallel plate capacitor, let's see if I can draw this in this thingy. This is terrible. So I got a parallel plate capacitor. The capacitance is, this is the distance between the plates. It is the area of the plates. It's epsilon, which is a material property, A over D. And the A in this case is W times L. So if I can make the area of the transistor smaller, I can make the capacitance smaller, and I can run them faster. So that's one place where I can pick up a freebie by using the multi-billion-dollar process to make things smaller. Yeah, it takes a while to get to the point where this is automatic. Just practice. But you get better, and nobody expects you to know everything your first day at work. At one of the things they told Corey, who was this he's the standard bearer for the college. Okay. He's graduating. He's got a job at Micron, and he is just amazingly good at everything I've ever seen. And he got a job at Micron, and they basically told him, we don't expect you to be productive for about a year. You'll be learning. I mean, you will be doing a lot of things that will make you productive later on, but we're not going to get anything really useful out of you until after that first year. So we're going to put a lot into training you. We're going to put a lot into helping you get up that curve, and but after a year, we expect you to be able to do stuff. And I'm surprised. Corey can do anything, or at least that's my opinion. So there's two ways we calculate delay. We don't actually do this in this class, but I'm going to kind of give you a preview. They're all approximations. For hand calculations, we get to do this in 380, Lab 1. There's the average current method, and this is in the Cedra Smith book if you're really interested in the details. And there's another one in here called the equivalent resistance based upon velocity saturation. They're not accurate, and when you calculate them, I think they come out to be like a factor of 2 or 3 apart. And when you calculate them and then measure them in the 380 lab, you might be off by a factor of 10. They're not very accurate. It kind of gets you in the ballpark, and it gives you an idea of what you can change if you want to make the speed faster. So if you look at the equations, the things that are in the equations, like the C in the numerator, I make that smaller, my delays are faster. The delay is proportional to the capacitance over W, but remember the capacitance is a function of W because it's epsilon WL over T. To really get accurate at the voltages you're talking about, you use something called ELDO is the Mentor graphics simulator. It's a bit more accurate than multisim, or Cadence, something like that, to get a really good estimate of what it's going to be. And of course, once you get the devices off the line, the processing variations that day, you recalculate them again, you remeasure them again, they're going to be different. So don't expect razor sharp precision on your timing delays. I added this morning. What is mobility? It's usually written as a mu. So there's an N-type mobility and there's a P-type mobility. And mobility is defined by this equation. If I put an electric field on the device, what is the velocity of the carriers? And we're talking about electrons. And I can calculate that by treating mobility like it's a constant. And it's constant for low values of electric field. So mobility is really defined by this equation. It is the put so many volts per meter, volts per centimeter in, electric fields in volts per centimeter, increase the voltage, I get faster electrons. And they roughly go up, the speed roughly goes up according to more volts, the speed goes up by the same factor. Okay, I put this in to explain the next slide, which is velocity saturation. So this is the curve for Vn equals mu Ne. And you can see if it's actually measured, the approximation pretty much holds true until I get up to around 10 to the 7th centimeters per second. And of course, I had to just go through and calculate that and compare that to the speed of light. It's about 0.01, it's like 0.01% of the speed of light. So at that speed, the electrons are, remember, they're not moving in a vacuum, they're not moving in free space, they're moving through a solid. So as they move through the solid very rapidly, they're more likely to hit something and lose momentum and bounce back and go in another direction for a while, and the electric field will kick them back out again. It slows them down. And so this is what's happening here, a semi-relativistic effect, limited by bouncing things off the crystal. And they get this slide once more again. I don't want to talk about it. Oh, power dissipation. This is the absolute last topic. The static power, if I leave the inverter with a 0 on its input and a 1 on its output, I get almost 0 power because I've got one really high resistance in series with a really low resistance. And this is always a high resistance to ground. So I'm generating almost 0 power. I mean, it's getting bigger because with the smaller L devices, I get more leakage current, which means that this high R is going down. So I'm getting more current between VDD and ground. The dynamic power is really what dominates. And you're going to learn the great mystery of life, one of the great equations right up there with V equals IR. And when we get there, and the short circuit current is another factor. It's small, it's increasing with shorter L, and it's a very significant part of the current when you get to power circuits. When you're switching kiloamps, this short circuit current is deadly. I mean, it can cause parts to explode and all that good stuff. So basically, if I'm sitting here like this, and it's always 0, this transistor is going to be off. This one's going to be on. This is such a high resistance, and then all I'm doing is sitting here storing this charge across here. Pretty much my P is going to approximately equal 0. If I'm sitting here with a logic 1, I've got this transistor is off, this transistor is on, I've got a high resistance to ground, the power approximately equals 0. Yeah, there's some leakage current, but it's not huge. It's a really good rough approximation of 0. Because it's dominated by this problem. What happens here, I'm switching, okay, that's just my stylus acting up. Let me see if I can do this and this will work. Yes, it does. Oh, I think I've got a mystery solved. Okay, if I'm switching between 0 and VDD, okay, so this means the output's going from VDD to 0. This capacitor is initially charged. There's got to be some, and I've got to take the charge off of this capacitor and take it down to 0. So the charge has to move, and moving charge is current. Current is defined as coulombs per second, amount of charge per second, dq dt. So I've got current flowing every time I switch. If my output's going, my input's going high to low, my output's going low to high. Now I have to charge this capacitor and put Q on it. So this is going to be where I get the current, is charging and discharging the capacitive load of whatever I'm driving with this inverter, which is more MOSFETs, which are more capacitors. Okay, that's conceptually. When they derive this in the book, but this is just like so fundamental. This is like Ohm's law. The dynamic power dissipation equals, is going to come out when you do the calculations to be, if I switch it faster, it's going to consume more power. If I'm driving more capacitance, I have a bigger charge to charge and discharge. It's going to consume more power. And it also goes up with VDD squared. So if I want to get the power down for free, there's three things I can do. The most fundamental things I can do. I can lower the frequency, which my cat videos load slower. I can decrease the capacitance by making the W times L, the overall dimensions of the devices, smaller. So I can make my process smaller, and then maybe keep the speed, bump the speed up a little bit higher and get the same power dissipation. But the biggest thing, and this has been going on like in my lifetime, VDD squared. Power goes down as VDD squared. So the old TTL parts that you used in the 110 lab, 5-volt logic, that was standard until the early 80s. Late 80s. And then they went down to, we're going to use CMOS, and we're going to go down to 3.3 logic. The power went down by a factor of 3.3 squared over 5 squared. Instantly free. You had to lower the threshold voltages on those transistors, which meant you made smaller transistors. So this has been, they've been taking this to the logical conclusion. So now it's 3.3, 1.8, 1.2, 0.8 volt logic. And it keeps going down every time I put them together. Be careful. Now, this really happened in the lab this year. We had a board, and it was mixed logic between 3.3 volt parts and 1.2 volt parts. And they weren't paying attention, and they built the printed circuit board. And what did they do every time they every time they blew it up, is they fried the 1.2 volt part by putting 3.3 volts to it. You've got to be careful and have level translators between there, and really watch it, because there's a lot of variety out there now, depending upon what's going on. The dynamic power, what did it come out to be? You can do the calculation yourself too, but 32.4 microwatts running at 100 megahertz with this huge capacitance of 100 femtofarads and a VDD of 1.8. So all those things can be dropped, and I'm running out of time. And yeah, the short circuit current, basically the concept of this is the edges don't change abruptly. They take time to change. So there's this little bit of time in here where both transistors are on. You've turned on, your NMOS is on, and your PMOS is still on. You have a short circuit between VDD and ground, and you get a peak current right in between those switching times. There are ways to delay that, and you'll probably learn more about it in Dr. Yoromasu's class. If you're a power person, not so much in my classes, but if you're an electronics person, if you're a programming, digital, signal processing, whatever the other people do, then you don't learn it yet. You don't care. Electrical engineering is a big field. Okay. All right, I'm done. Any questions or other stuff?
Velocity, saturation.
Hold on a second. That Ibrahim, are you here? Austin Arnis, if I missed you, just Lauren and Jordy. Okay. Nobody's barking at me. Okay, so fiber optic cables, they're actually bundles of cables. And they have one little cable going through there is a fiber. And wait, what was the question?
So velocity saturation is on a optic.
Oh, okay, so the velocity through a fiber optic cable, it's going to be the speed of light. There is no electrons moving through there at all. It's photons moving through there. Now, the issue with a lot of the cables is dispersion, because the index of refraction of the cable is different for different wavelengths of light. So which means that different wavelengths of light move through the cable at a different speed. So you have to, if you want to do any broadband communication, you've got to have a very low dispersion cable in order to get everything across there. Yeah. Individual fibers aren't that big. It's just the processing control on the materials is amazing to get. Yeah. I get to play with that next year. I've got to, this is my task for next year. I've got to put one photon through and get it out the other side. And then polarize it and still get it out the other side. And then change the frequency and still get it out the other side. At about a one photon per 10,000 photons per second. That's about the speed.
Hey, Ms. Julie.
Yes.
Yeah, I have 2 questions.
Okay.
Yeah, one of them is about the lab today that I had to leave earlier.
Okay.
And I have sent an email to Vinod, but he didn't answer yet.
Okay, so that's entirely possible because Vinod's a grad student, and so
Yeah.
he's taking classes and he's working on his project and he's doing a whole lot of stuff too. So it may take him a day before he checks his email. I wouldn't be surprised.
Because it's regarding for lab 4, which is due Friday. So
Okay.
if you could talk with him to maybe respond earlier.
Okay. If the best thing to do would be to just email the question to me, and I'll answer
Okay.
first thing in the morning.
Okay. And the other thing is about the exam too.
Right.
So if I want to take it by remotely, when it will be?
Send me an email. I've got a list in my office and I've got the time written down on it. So
Okay.
best just send me an email.
No problem. Thank you so much.
Okay, no problem.
You have a good day.
Okay, you too. Okay. Oh, somebody's in chat. Yes, that works, Jordan. Yeah, just tell me you need to take it online, and I'll try to set up a time where that's agreeable to both of us. I have a default time already planned, and if that doesn't work for you, then we can work around that within the limits of I can't be in class or asleep in the middle of the night. Okay, it is, what is today? Oh, it's Wednesday. And we don't have any, oh yeah, I do. I have food. Food feed. Oh, I should probably just like stop recording if everybody's gone. Stop share. And bye.